This video, we're going to actually figure out how to calculate the work that you've done for more complicated situations. And when I say calculate the work you've done, I mean it in physics sense. You can't use this to prove that you're doing more work on the dishes than your little brother. Instead, what this means is how much energy are you putting into the system, or how much energy are you taking out of the system. So let's look at this a little bit. So let's start with the standard example. If we just have a block, and it's traveling some distance, and there's some force being exerted in the same direction, then we can just say work equals force times distance. But what about more complicated situations? Last lecture we showed you have to use a little bit of trigonometry. If there's an angle, if the force is at some angle to the direction being traveled, then you can use a cosine. So we can say that work equals force times distance, and only force that's parallel to the distance. So what we can then say is work equals force times cosine of theta times distance, and that'll give us the work. But what about complicated situations where let's say there's friction on the box going in the opposite direction? Does the friction count as work, or is it its own work, or what's going on? So to understand an example with friction, let's first do friction on its own. There's a box sliding along, and it has some velocity to travel some distance, d. But the friction is exerting a backwards force on the box. Now we could say, well, it's traveled some distance d. The friction is parallel to the distance, just in the opposite direction. So the work just equals force times distance, right? Simple as that. Well, that's not quite true. The force is in the opposite direction of the distance. And if we plug that into the cosine, if we said cosine of 180, we'd actually get -1, not 1. So it's not that simple. If the force is in the opposite direction, the work is negative. So what does that mean? Well, that means we're taking energy out of the system, not putting it into it. This makes a lot of sense. If water's flowing along, and it meets a water wheel. The water wheel is exerting a backwards force on the water, but the water's flowing in the forwards direction. So the water wheel is taking energy out of the water's flowing more slowly now. And instead, it's putting energy into something else. It's gathering the energy to turn into electricity, or to grind corn, or something like that. So what that means is, if the force is in the opposite direction of the work, then it's negative. So in our more complicated example, we have someone dragging a suitcase behind them, and they're exerting a force in the forward direction, and friction is exerting a force in the backward direction. So we'll have force of friction and force of pull. I'll use letters to represent that. Then what we mean by that is the force of pull is putting work into the box, even if it's not accelerating. And the force of friction is taking work out of the box. And if the box isn't accelerating, if the net force equals 0, then what you'll find is the energy flowing into the box is exactly the same as the energy flowing out of the box. And how is this? Well, there's a force of pull, and it's times some distance d that the box traveled. So the work going in is just force of pull times distance. And we know it's going in because it's positive. And the work going out is force of friction times distance. But wait, it's in opposite direction, so that's negative. So if we add the work going in to the work going out, we'll find out that if the force of friction equals the force of pull, distance equals the same. So we end up with distance times force of pull minus force of friction. Force of pull minus force of friction is 0. So that's 0. So as a result, the work in plus the work out equals 0. So the work in equals the negative work out. So the amount going in is the same as the amount coming out. And this same simple logic can be applied to even more complicated situations. For instance, now imagine there's gravity pulling down. There's a normal force pushing it up. Friction's going backwards. And the force of pull is going at an angle. So now we need to figure out exactly what's going on here. We can break the force of the pull down into the x and y components using the cosine, and look back at the last video if you don't remember how to do that. And what we'll see is because the box isn't rising up into the air and it isn't sinking into the ground. We know the force of friction, we know the force of normal plus the force in the y direction has to equal force of gravity. And since all those are perpendicular to the direction of motion, which is still horizontal, we can conclude that all of that has a work of 0. Which leads us to the interesting stuff. That's the force of friction and the force in the x direction. And both of those do work. Now let's say they balance out. Then the box isn't accelerating. And from earlier lectures, it seemed like, well, when the box is accelerating, that's how you know work is being done. So does that mean no work is being done? And that's really not the case. Because if you left the box on its own, it's not accelerating, but it has some velocity. And if you left it on its own, you didn't exert a force on it. Then what you'd find is it would decelerate. Because then the force of friction would be unopposed. There'd be no force of pull. And as a result, it would come to a stop much more quickly than a box that was being pulled, at least for a while. The box being pulled is going to continue on for much longer. So as a result, even though there's no acceleration, pulling on the box still makes an impact on the system. So there's still work being done. So if you ever get confused, take a pause, draw a free body diagram, label all of your forces, break them down into perpendicular and parallel components like we did here with the force in the x direction and the force in the y direction. You can safely ignore the ones that are perpendicular to the direction. So we can ignore that one. And then the ones that are doing positive work are putting energy into the system. And the ones that are doing negative work are pulling energy out of the system. And depending on whether more energy is coming in or out, the box will speed up or slow down, rise up or drop down. So hopefully that made at least a little bit of sense. If not, go back, look over it again. And if you got it, you're ready to move on to the next lecture.